so much, Mr. Chairman. Good morning to everyone. My work deals with notch components under non-localized creeping condition, and I will show you a numerical evaluation of stresses and strains. I did this work when I was a PhD student at the University of Padua, before to move to other university just a few months ago for a postdoc. So my work takes inspiration from a previous job made by Professor Glinka and Nuñez regarding the same method I'm going to show you here, but limited to U-shaped notches. So together with Professor Glinka, we decided to extend his method, his approach to V-notched components, so to a larger variety of notch geometry. So I'm going to show you brief outlines. First, we will speak about the Nuñez-Glinka approach, just because we use the same main equation. So I'm not going to show you all the analytical frame for the sake of brevity, but I will focus more on the concept and on the ideas behind our method. Brief introduction about Lazarenko equation, because Lazarenko equations are the key to extend the Nuñez-Glinka approach to a larger variety of notches. We're going to see in detail the extension, and also we will compare the results from the numerical. We will compare the numerical results and the finite element analysis. In the end, I will conclude with some final comments. First, for non-localized creeping condition, we mean a situation in which all the material far from the stress concentration zone may creep as well. So we need to take into account the contribution of the far field to the notch tip deformation. So, just a few words about the motivation. We know that geometrical discontinuities such as notches need to be carefully analyzed. The knowledge of strains and stresses in such stress concentration zone is essential for an efficient and safe design process. It appears from the current literature that needed are numerical or analytical tools enabling the analysis and simulation of creep deformation near notches. We would like to provide strains and stresses ahead of notches that can be used as input parameters for creep models for strain and fracture evaluation. So, briefly, the Nuñez-Glinka approach has some assumptions. The most important one are that it was based on the number rule extended to time-dependent problems and on the equivalence of the total strain energy density at the notch tip. Putting together these two hypotheses, they evaluated a set of equations to be solved numerically. For the elastic stress-strain distribution, Nuñez-Glinka employed the Krieger-Parry equation. So their method is limited to U-shaped notches, because the Krieger-Parry equation are valid just for U-shaped notches. The set of equations to be solved numerically are the one shown in this slide. As I told you, I'm not going in details in the analytical frame for the sake of brevity. These equations are the same equation that we used also in our method. We just changed, as I will show you later, the linear elastic equation. So we changed the definition of some parameters in this equation. So we have the increment of the creep strain, the decrement of the stress due to creep, and the increment of the total strain. The most important one is the decrement of stress due to creep. As you can see, we have a lot of variables, but the most important one is this factor. This factor represents the effect of the far field creep on the notch stresses and strains. So it's like we are considering here the far field effect as an extra energy input to the notch. So we are evaluating the total strain energy density far from the notches, and we magnify it through the same energy density concentration factor, that is the ratio between the total strain energy density of close to the notch and the total strain energy density in the far field in the elastic field. So we added this magnification effect to the total strain energy density at the notch creep. We have another important parameter, that is the plastic zone correction factor. It was defined by Glinka following also the Ewing's definitions. We need to define also the meaning of far field creep. Glinka suggests to take the far field contribution 3 times at a distance that is equivalent to 3 times the notch radius. In our method, we cannot use 3 times the notch radius as a constant distance, because if we are going to move to more sharp notches, this distance becomes too much short. This is valid for tension loading. In case of bending, Glinka suggests is 1/2 of the nominal stress. So this is the very simplified time integration algorithm of Nuñez-Glinka. So we have to evaluate the linear elastic contribution, employ in this case the Grigor-Parry equation, and also the first elastic plastic contribution. In this case, employ the number rule, but we can also use, for example, the equivalent strain energy density or simple finite element analysis. After that, we evaluate the creep strain, the stress decrement due to creep, the total strain, and we repeat this time integration until we reach the total time t. The Nuñez-Glinka approach, as I already told you, was limited to U-shaped notches because of the employment of the Grigor-Parry equation. So our idea was to use the Lazzarinto equation instead of the Grigor-Parry equation. The Lazzarinto equations are a more general formulation of the stresses and strains distribution ahead of notches. It can be applied to U-shaped notches, to blunt or to sharp notches, and also even to cracks. So the Grigor-Parry equation are like a specific solution of this equation. Redefining, of course, the elastic distribution, we need to redefine all the parameters that we saw in the previous equations. The most important is the definition of the plastic zone correction factor, that in turn is a function of the plastic radius and of the increment of the plastic radius. As I told you, as a function of the geometries, we need also to change the evaluation of the far field distance d. So, how to define the plastic zone correction factor and the plastic radius? Once imposed a yielding condition, together with the equation of Tau-Lazzarin, we can obtain a first approximation of the plastic radius. After that, assuming an elastic plastic behavior of the material inside the plastic zone, we can carry out a simple equilibrium of forces within the force F1 and the force F2. So in this case, we can obtain, solving this integral, a first approximation of the plastic radius increment as a function of F1. Once we have the plastic radius and the increment of plastic radius due to stress redistribution, we can evaluate the plastic zone correction factor as defined by Glinka and also by Irwin in previous work. As you can see, with simple substitution, we can obtain the explicit formulations. I'm not going into details here for the sake of brevity. Let's say that also if these equations become a little more complicated, employ the Lazzarinto equations. Once this method is implemented in a numerical tools, for example, MATLAB, as we did, this equation can be easily solved in a very easy and fast way. So it's like an automatic process. We don't have to evaluate this equation each time. So we employ the same simplified integration algorithm, but in this case we use the equation of Lazzarinto. After that, the procedure remains the same, so we have to evaluate a first initial elastoplastic contribution, for example the number rule. After that, the creep strain, the decrement of the stress due to creep, the total strain, and we repeat over all the time t. We implemented our method in the MATLAB code, and we compare the results obtained from the numerical viewpoint to a finite element analysis carried out through ANSYS APDF. These are the material properties that we employ, and we consider several notch geometries. You can see here the details. So we varied the depth of the notch, also the notch radius, moving also to small notch radius just to see the effect of these parameters, and also different opening angles. Let's see now the results. As we can see, we have the theoretical solution that is very close to the finite element analysis. For a theoretical solution, I mean the results obtained from our numerical method. We have a difference of about 9% for very large time t, and of about 5% instead for very small time t. These results are just a selection of such geometries, just to show you the fork of the errors of our method, so to show you the best and the worst the worst results. We can see another case. For example, here we have a difference of about 9% and here of about 8% for small time t. Regarding instead the stride, the situation is a little better. We have an error of about 3% for low time t. And if we change geometry, we have in this case 40% of error for very large time, but only 4% for very small time. So most of the errors is always localized for very large time t. So summarizing, the Nuñez-Glinka method was limited to notches and has been here extended to a wide variety of notches. The key to employ this extension was to select the Lazaretto equations to describe the early elastic state of the system. The numerical and finite element analysis show a very good agreement within the theoretical and the finite element results. The higher values of the errors have been found for very large time t, mainly because of extensive plastic, plastic deformation. If we neglect the far field contribution, we can easily derive also the localized gripping condition, so a situation in which we don't have any influence from the far field grip. Our notch tip stresses and strains can be employed as input into stress-strain pre-models for strain and fracture evaluation. With our approach, we don't need any more time-consuming nonlinear analysis. We just have to employ the numerical method. As a future development, we know that local approaches based on stresses and strains fail when the stress fields tend toward infinity, so for example cracks or very sharp notches. So also if Lazaretto equations are valid in this situation, we cannot employ anymore the local stresses and strains. So our idea is to move to an average strain energy density rate as a pre-design parameters. We obtained some preliminary analysis just to understand if there is any meaning to try to propose an average strain energy density in this case. So try to understand if we have the same advantages that we have for linear elastic assessment with the strain energy density. I cannot show you here these results for the sake of brevity, so we will see maybe in the next ACF. Thank you so much. Without any power electricity loss, so I'm very glad. Thank you.